in the Rambo, I'll teach quantum field theory for you. And so here is the plan of the course. So first, some organizational things. So first, I suggest to make a break in the middle, like for 2 minutes or so. That's tough to sit in for 2 hours in the class. Then I encourage you to ask questions if you don't understand something or understand too well. If you more feel like to if it's easier for you to ask questions in writing, you can just write it on the sheet of paper and send to me. I'll answer them. And I think there is some organized way to sort of write these questions and submit through people who organize this course, but you can do it in the class as well. So what is this subject of quantum field theory about? Well, field is something that is defined everywhere in space and at each moment in time. Oh, we have some variables that depend on time and on the position in space. And we want to apply rules of quantum mechanics to such systems where the field variable becomes an operator. So, of course, you know a lot of examples of fields, electric fields and magnetic fields, or metric in gravity is another example of the field, or in fluid dynamics, velocity and density of a fluid are also fields. So it's a very general framework. And in principle, it's easy to apply the rules of quantum mechanics to such systems. I mean, not easy, but it is a straightforward thing to do. But the consequences are quite interesting and also lead to rather general conclusions. Namely, quantum field simultaneously describes waves, which is obvious, of course. Any field equation like Maxwell's equations describes waves, propagation of electromagnetic waves, for instance. But when we quantize them, it turns out that they also describe particles. So an electromagnetic wave, as you know, can be viewed as a collection of photons. And this is a general phenomenon. So there is the quantum field describes particles. Another thing that is probably less obvious is that quantum field also describes forces. And all in the unified way. So there is, in principle, no physical distinction between waves, particles, and forces in this framework. So our main goal will be, well, relativistic field theory. That's is a modern basis for particle physics. So the great deal of quantum field theory is how to maintain Lorentz invariance in all the equations, etc., etc. So this will be the major, more important part of the course. However, I'll start with a with a set of non-relativistic examples, which hopefully would be easier for your intuition. Because, of course, I mean, you know what is particle, what is wave, etc., etc. And I'll try to relate all of these things for you by considering some simple examples. So first example will be, we'll consider a method that's used in a lot in condensed matter physics, namely second quantization. And it directly leads to the notion of quantum field. So, well, how do we describe particles? Well, of course, we know how to do it in quantum mechanics. We just need to write down the Hamiltonian. So let's consider a Hamiltonian that describes a collection of particles that interact pairwise. So we have well, the Hamiltonian is the sum of kinetic energy plus potential energy, and the potential energy will take in the form of sum of pairwise interactions. So what do we do with this Hamiltonian? We can easily write down the Schrödinger equation for it. But if you imagine that the number of particles here is 10 to the 23, or even, I don't know, a few hundreds, then solving this equation will be hopeless, even with a computer. But obviously, this is a situation that happens many times in physics. Like if you want to describe electrons in a piece of metal, this is a first model to start. And then the usual rules of quantum mechanics based on Schrödinger equation are not adequate. One should devise something else, and the method to use is known as second quantization. So the idea is basically similar to what we do in statistical mechanics. So if you have a lot of particles, it is useful to consider particle number as a variable. So consider grand canonical ensemble instead of canonical ensemble. And something similar we can do in quantum mechanics as well. So our first goal will be to understand how to deal with with the system described by this Hamiltonian, but making the particle number a variable. So, well, let us first consider the case where this term is absent, so that we only have kinetic energy, so we have a set of free particles. And then, of course, we know how to solve the problem. The eigen functions of this Hamiltonian will be plane waves. And depending on the particle statistics, we will need to either symmetrize or anti-symmetrize the wave function. So the wave function will be characterized by a set of occupied moment of particles. And we can write down the wave function, say, in coordinate representation for this state by, well, taking a sum of all permutations of particles. Okay, so this is a pretty explicit expression. So the plus sign corresponds to bosons and the minus sign to fermions. So the particles can have one of the two types of statistics. And so this is the answer. But now we want to write it in a way that is useful when particles start to interact. So what we do is we consider, so we enlarge the Hilbert space on which our operators act by considering the whole collection of states with arbitrary number of particles. So this is called Fock space. And the Fock space is, well, it consists of an empty state. So this is just a state with no particles. Then state with one particle, state with two particles, and so on. So we take a linear envelope of all possible states that contain arbitrary number of particles. Now, of course, the number of particles is conserved, so the Hamiltonian will act, in a sense, horizontally in this space. So it will not mix states with different numbers of particles. But yet it is convenient to introduce operators that jump between different levels in the Fock space so that they change the number of particles. So the basic operator of this type is the creation operator. Which acts in the following way. So if we have a state with n particles, the creation operator will add another particle with some definite momentum p. So in principle, having this operator, we can reconstruct all the Hilbert space starting from the ground state, because starting from the empty state, okay, so if we apply the creation operator n times, we reconstruct the state with n particles. So we add them just one by one with the help of the creation operators. Now, why do I write the dagger here? Well, it is just a matter of convention, but it sort of suggests that there is a conjugate operator to the creation operator that is also useful. Yes?
Are we implicitly, or maybe I missed this and maybe explicitly, describing just bosons?
Not necessarily.
Isn't that for fermions a normalization, or a constant factor outside if you operate on?
Not in this formula. So this formula is the same for bosons and fermions. I'll explicitly tell you which formula corresponds to bosons, which for fermions. So, now, of course, these states are, well, they have a very explicit form in, say, in coordinate representation. So we know how to compute an overlap of these states, and it's a matter of simple calculation to see that they are delta function normalized, right? So they are equal to 0 if momenta are different, and well, is normalized to the delta function if they are equal. So we know the scalar product between any of these two states And so that's enough to calculate the Hermitian conjugate of this operator, right? So we just need to take an overlap of this state with another state in the Fock space, take complex conjugate, and this will define the matrix element of the Hermitian conjugate operator. So I'll not go through all of this, but we'll just give you the final result. So it turns out that the conjugate of the creation operator, well, it's is an annihilation operator which removes one of those particles, provided that the momentum p is equal to one of those momenta. That's equal to 2 pi h bar cubed. And then we should sum over all particles in the state. And so if p is equal to one of the momenta, pk, then we should remove the particle. And here we need to introduce the statistics factor. So the formula is a little bit different for bosons and for fermions. And so the hat means that we just cross this momenta. It's not present anymore in the state. Okay, so from these two formulas, so we know how our operators act on an arbitrary state. We can thus find, say, the commutator of these two operators, and the commutator has a very simple form. So if we commute AP with A dagger Q, then the commutator will be equal to 2 pi h bar cubed times the delta function. Again, I do not give a derivation, but it's an easy exercise based on these two formulas. So this formula is varied for bosons. For fermions, a natural object is an anti-commutator of creation and annihilation operators. And again, it's equal to 2 pi h bar times the delta function. So the anti-commutator is defined as for two operators, it's given by AB plus BA. And then if we, say, commute two creation operators or two annihilation operators, then we get 0 for bosons. And then for fermions, they anti-commute. Okay, so what's the use of these operators? Well, we can use them to, well, represent all of our operators. Yes? Yes, but you can very easily understand what would be the difference in d dimensions. So the only place which will change is the power of 3 to pi h bar. Okay, so for instance, the free Hamiltonian the one without the potential part can be written as an integral over all momenta then the energy of a particle with this momentum, and then times the product of creation and annihilation operators. So why does this formula work? Well, this operator measures the number of particles with momentum p in an arbitrary state. So if we act with it on a state with an arbitrary number of particles, it will return the number of particles that have momentum p in this state. Because, so first we, if there are no particles with momentum p, the annihilation operator will kill the state. And if there is a particle, then annihilation operator will be removed, but then we'll recover this particle with this creation operator. So it will produce just the number of particles with that given momentum. And so this integral just measures how many particles have this particular momentum with the weight, which is the energy of the particle with momentum p. So it gives the total energy of the state as a sum of, as a sum of all overall particles of their one particle energies. Okay, so now our next goal will be to understand how to, well, in a sense, we knew in advance how to solve this problem. It's very, very simple. But now we want to add interactions. And when we add interactions, then this formalism based on creation and annihilation operators becomes really useful. In particular, it's very useful to make a Fourier transform to the coordinate space. So let's try to see what we get if we go into the X representation just for these basic operators. So we can introduce an object which we'll call psi of x, which is just the Fourier transform of the annihilation operator. And its conjugate is Fourier transform the creation operator. So this operator is called field operator. So this is how quantum fields arise in this multi-particle problem. So what's the physical meaning of these operators? The physical meaning is that they create and annihilate particles in a given point in space, right? Because so these operators, they create and annihilate particles with given momentum. And so when we do Fourier transform, we, from something that has definite momentum, we get something that has definite coordinate. Yes?
It looks like after the Fourier transform, the position plays the role of a variable, whereas before when we were considering a momentum representation, it looked like momentum was a parameter rather than a variable.
Yeah, it's exactly. So yes, so here P and X are parameters. They're not operators anymore. So they're just parameters. So there's C numbers in this sense.
So there, it looks like P is a parameter because it's a subscript, and down here X looks like a variable because it's in parentheses. Does that have any significance or not?
Yeah, it's probably, actually it would have been better to write it as a subscript here as well. But at the end, it doesn't matter. So it's just a more conventional thing to write it in parentheses as a argument of operator valued function. But yeah, the meaning of this is just as it's a parameter that labels our operators. So what we get is an operator valued function. So it's an operator that's defined at any point in space. And we know how this operator acts in our states. So let's see what we get by acting with, say, creation operator on an empty state. So I will denote this by x. So let's consider this state. So the claim is that this state describes particle at point x. So it's just, yeah, so one particle state, which is an eigenstate of the position operator in the old formulation where x and p were operators. To see this, we can take an overlap of momentum eigenstate of one particle with this new state that we called x. So this was just a definition. And now we can calculate what it is. So we introduced the, so psi dagger was a Fourier transform of the annihilation operator. And then we have a matrix element of this form. I see that there are too many objects are denoted by the same letter. So let's denote the integration variable by q. So then we have aq here acting on the empty state. But then by construction, this state is just an eigenstate q, and the overlap is simply the delta function. Let's see. So there is a factor of 2 pi. And then, the momentum eigenfunctions are normalized to 2 pi h bar in our notation. So this is equal to the integral of d3q 2 pi h bar cubed, and then e to the minus I q h bar q x divided by h bar, and then 2 pi h bar cubed times the delta function of p minus q. And so we just use the delta function to perform the integration. So this is equal to minus I ex over h bar. And this is, in a sense, is a definition of what we call a momentum eigenstate. It is something, an overlap of which with the momentum eigenstate produces the plane wave. Okay? So from that we conclude that x is the momentum eigenstate. So this operator creates a particle located at whose wave function is concentrated at point x. So we can also create a set of particles with given positions if we apply n operators of this type. And so the field operator, in fact, creates a particle at a given position. So this is the conclusion of this calculation, we can also figure out what are the commutation relations of the field operators. So if you commute psi of x with psi dagger of y, well, what we get is the delta function of x and y. And for fermions, we should anti-commute these operators to get something reasonable. So this is sort of a way to go from momentum to coordinate representation. So why is it useful? Well, one reason why is it useful is that using these field operators, we can easily calculate what is an image of an operator that is sum over one particle, well, operators. Let me write down the formulas, and it will probably become more clear. So, so in quantum mechanics of one particle, suppose that you have some operator that is a function of particles' momentum and coordinate, and you want to calculate a matrix element of this operator in some state. And we know the wave function of the state in the X representation. Well, then what we do is we integrate over the whole space of F, where we replace X by I h bar d over dx, I guess with the minus, and then x, and this should act as a differential operator on psi of x, and then we should integrate. Now there is a nice analog of this formula in the second quantized framework. And this formula looks like that. So suppose that you have an operator, let's call it F, which acts on each particle at a time. So it is a sum of operators that act on each of the particles. Then, okay, so we can introduce creation and annihilation operators and the field operators. The claim is that F then has precisely the same form as this matrix element. So we can write that F is equal to the integral over the whole space psi dagger of x then f of minus I h bar d over dx x, and then acting on phi of x. So precisely the same formula. But now the meaning is different. So here, psi was a wave function which was just a C number function. And here, psi is an operator. So let me denote this by putting a hat over it. Hope it doesn't lead to confusion. So it's a bit tiresome to write hats all the time. So all these psi's are operators here, and here as well. So in some sense, when we go from one particle problem to many body problem, what happens is that we can, and we are dealing with operators of this type, then what we need to do is we just replace the wave function by the field operator. And so promote the wave function to an operator in some sense. So this, well, this simple observation gave a name to this framework, namely the second quantization, because if we start with a classical system, what we do is we replace dynamical variables such as coordinates and momentum by operators. And here, when we go from one body problem to many body problem, we replace the wave function by an operator that satisfies such and such commutation relations. And then we can write the operators in this representation where we have operators acting on each particle by operators that now act in the Fock space. Okay, so this psi acts in the Fock space, which may contain, and the states in which may contain an arbitrary number of particles. So let me give two examples of this formula. So the first example is the free Hamiltonian. So for the free Hamiltonian, we have the following representation. Which is is obtained from this formula. So we first replace pi by the gradient, and then what we do is we integrate by parts. Okay, so to go from this formula to this formula, we integrate by parts, and then one derivative acts on psi dagger and the other on the psi. On the other hand, the same formula can be obtained from, let me see it, from this formula, just by Fourier transform. So if you Fourier transform A dagger and A, you will eventually arrive at this equation. So now the second example is just the unit operator. So in this case, F was equal to the kinetic energy. Now let's take the sort of trivial example when F is equal to 1. And so then this operator just measures the number of particles. So it's F is equal to n. And so the particle number is given by the integral over the whole space of psi dagger psi. So first of all, well, the particle number was a number. Now on the right hand side, you have an operator. So in the second quantized framework, as you see, the particle number has become an operator. So this is because we allowed the states with different number of particles. And although in any given problem that we want to solve, the particle number may be conserved, if we want to solve it for arbitrary n, then it is convenient to think of n as an operator as well. But it's just as usual. We have the basis. In the basis where our problem was originally formulated, this operator had, was diagonal. So this formula shows that it's convenient to introduce so that this product has a meaning of the particle density. So what it measures is literally the density, the number of particles at point x. Okay, so, and this is analogous to the usual formula in one-particle quantum mechanics, where the wave function squared is a probability to find this particle at point x, right? So now here, in a sense, this is also a probability to, but now we have n particles, so this just tells us how many of these particles are sitting at point x. So now let's return to the problem that we wanted to analyze from the start, namely the problem of interacting particles. So when the Hamiltonian was given by the formula over there, so we have n particles that are interacting pairwise with a given potential. So how do we write the second quantized version of this? Well, we know already how to write a second quantized version of the kinetic energy. So for the potential energy, we can just make a guess and then check that it's correct. So if we have, say, okay, so if you consider just two particles and interactions among them, so if each of the particles is described by some wave packet, so there is wave packet of particle 1, and then the wave packet of particle 2, then the interaction energy will be equal to psi 1 of x squared, and then the potential of interaction, and then the probability to find the second particle at point y, and then we should integrate over x and y, okay? So this would be a natural expression for the interaction between two quantum particles with wave functions psi 1 and psi 2. Now, in the second quantized framework, we should replace psi's by operators. So what we should write is an analog of this formula. So let me just write down the right answer and then explain what it means. Okay, so this is basically the same formula, except for two differences. So one difference is that, okay, so rho is the same, is the density operator, and it has precisely the same form as psi by psi. So this is psi bar psi inserted at point x, and then psi bar psi at point y, and weighted with the interaction energy. But then there is a factor of 1/2. Well, why is that? Well, the reason is that the particles here are undistinguishable, so they're all the same. And if we write this formula, we will count, we'll double count, right? Because we cannot tell which particle is particle number 1 and which is number 2. So they are described by one and the same field operator. Okay, so we need to divide by 2 to avoid double counting. The second difference is more subtle, and it has to do with the fact that we promoted wave functions to operators which do not commute, right? So they satisfy non-trivial commutation or anti-commutation relations. And so the answer in principle will depend on how you order these operators. So the ordering here is really important because we will get different answers depending on which operators will be put first and which will be put last. And so the correct answer corresponds to normal ordering. So normal ordering, well, here it is denoted by as semicolon. Normal order prescribes us to put all creation operators to the left of the annihilation operators. So whatever stands in the middle, the normal ordered expression tells us that the operator that is standing here has all psi daggers to the left of the psi's. So in particular, so what we have here is psi dagger x, psi x, psi dagger y, psi y, and then normal ordered. So by definition, we should put psi daggers to the left of psi's, not using commutation relations. So we can always do it by, if you don't have this ordering prescription, we can always do it. Use commutation or anti-commutation relations of this type to commute all the all psi daggers to the left. But the normal ordering means that we don't do it, we just put them to the left without producing commutators. So by definition, this is equal to psi dagger x, psi dagger y, psi of y, psi of x. Yes?
So, sorry, the ordering of the order of the coordinates becomes important when we talk about fermions. So
absolutely, yes. So that's right. So for fermions, the prescription is following. So you should reorder the operators here in such a way. So if you interchange fermions, you should produce a minus sign. So this expression is correct both for bosons and fermions because, okay, I interchanged these two operators and then psi of x with psi of y. So I did two interchanges. So if they were fermions, then I would produce minus 1 squared. If I want to write it as psi dagger x, psi dagger y, so let me write it like that. So this is equal to minus 1 plus minus 1 psi dagger x, psi dagger y, psi x, psi y. Yes? So this is just a prescription. This is a definition. So we define normal ordering by saying that we should write operators such that daggers are to the left. So the question is why we should use it in this formula. Well, this is a matter of checking if this reproduces the original Hamiltonian when acting on multi-particle states. So this will be one of the problems to do on tutorials. So you'll have to check that this operator gives the correct answer. So I'm writing it here without derivation. Yes?
So it does matter that you put the side y side x or side x.
Yes, it does matter. If the fermions, it matters.
Is it just a definition, or is there any meaning you put the side y first and side x?
Well, I can put them in the opposite order, but then for fermions, I should have changed sign. So if I want to, so the reason I wrote it like that, because this formula is then valid for both bosons and fermions without any signs. So in this form, there should be a sign factor. Any more questions? Well, then let's make a 5-minute break. Okay, so we reconvene at 10 sharp.